Hello friends, I am Sumit. This is my YouTube channel Masif. So today I'm going to talk about the saddle point. Uh, this is an interesting. Uh, this is the interesting. What should I say? Interesting concept which draws its name from something which is placed on the back of the horse. Uh, so saddle is the seat which we place on the back of the horse so that the rider can easily sit over it and enjoy his or her smooth ride. Okay, so saddle is that seat which we place on the back of the horse, and this is the sheer, this is the actual shape of saddle on which you, if you try to see at which point there is local maxima or local, basically saddle is one such three-dimensional figure where you won't find any local extreme or local maxima, either local maxima or local minima. Okay, if you are not able to understand few things, it's okay. I'm going to make it clear. I'm going to make it look very clear. Just have some patience. Before I proceed for the saddle point, let me put few things in perspective, because I'm going to presume that you may not be familiar with these things. If you are, that's good. Let me talk about local maxima or local minima. What is local maxima and what is local minima? So suppose this is the I'm going to take only two variables on two dimension board. So suppose this is the dependent variable and this is the independent variable. And if suppose the function looks like this, now you tell me what is the local maxima. Local maxima will be this value of, say, suppose this is y star. Okay, this is the local maxima. This x star, y star. This is the local maxima. The function attains its maximum value when x is equal to x star. And what is the maximum value? Function attains y star. Similarly, function, if the function would have looked like, if the function would have given this kind of shape for the curve. Suppose the function is this one, not this one. In that case, there is no local there is no local maxima, because it will go up and up, right? It will also go up and up. There is no local maximum, but definitely there is local minima. There is one minimum point. There is one minimum point, only one minimum point, and that is what, say, y dash, and it also comes at x is equal to x star. So x star comma y dash would be the local minima for this function, right? Now, but when we solve when we have a function, function would not be always this simple that we can draw it, right? It will be very complicated. So we should have we should have some rules handy, so that we can actually find out where the function would have maxima or minima. So that is nothing but, if we take the derivative, first order derivative or second order derivative, then looking at the first order derivative and second order derivative, we can tell where exactly the function has maximum or minimum. So I'm going to tell you that, and then I'll proceed for the saddle point. So you can see that the function in this case. Suppose remove this one. I'll draw this function later. Okay. Let's focus on this function. We can generalize to this local minima also. Then we may not need to talk about local minima. Let's take this function only. Okay. I can take that function also. No, not an issue. So in this case, if you see, if we increase the value of x, right, the value of y increases, right, and the value of y increases with increase in the unit of x. With each unit increase in x, it will increase and it will increase. It would have increased always, but it is increasing at a decreasing rate. So there will come a point where it will not increase, and there will come a point from where it will start decreasing. And the reason is that because it is increasing at a decreasing rate. Or in other words, the second order derivative is negative. What is first order derivative? That is your change in y upon change in x. What is second order derivative? Change in the change in y upon change in the change in x. Right? So the change is your second order derivative. Third order derivative is change in y upon change in x. Right? Now you see that first order derivative, y is definitely increasing with increase in x. So first order derivative is positive at this point. but here the y is not changing. It stays here only, right? At this point, the y is not changing. So the first order derivative will be 0. And from here, the first order derivative would start becoming negative. In a way, it is equivalent to say that y starts falling from x star onwards. So this is the case. So that's why we know. So one thing is that we can say that if the first order derivative is giving you 0, then that point can be either local maxima or minima. Because even in that case, the first order derivative was, so suppose in this, if the had the function been looked like this, even in that case, if you see, first order derivative would have been equal to 0 at this point, right? So if the first order derivative is equal to 0, then we can, it's not a sufficient condition, it's a necessary condition. I'll talk about where it may not hold true. Okay, so that's why it's a necessary condition. If it has to be either local maxima or local minima, then first order derivative has to be equal to 0. Now, what is the sufficient condition? Well, your second order derivative should be negative if it is a local maxima, and second order derivative has to be positive if it's a local minima. I'm just going to tell you why it holds true, why this condition holds true. You see, this function, at this point, your first order derivative is equal to 0. But at this point, what is your second order derivative? You don't need to look at this point. You start looking from here only. Even that would suffice. You see, the function is increasing, but the function is not like, the curve is not like this. Curve is looks like this. If had it looked like this, had it looked like this, in that case I would have said the function is increasing at an increasing rate, or the second order derivative is positive. But in this case, the function is increasing but at a decreasing rate. Decreasing rate means whenever we increase x, the value y increase, fine. But every successive increase in x does not increase y at such pace where it increased when we increase the unit of x previously. You're trying to understand what I'm trying to tell you. The y is increasing, but look at this way. It looks like this, right? It doesn't look like this. Had it looked like this only, then it would have increased at a constant rate. If it looks like this, then it is increasing at a decreasing rate. If it looks like this, then it is increasing at an increasing rate. In this case, since it is increasing at a decreasing rate, so there will come a point where the pace will stop and the function will not increase at all, or it will rather not change at all. That is here. And since it is still, it was supposed to increase at a decreasing rate, so there will come a point where it will not change at all, and same thing would repeat in the next like with successive increase in x. After that point onwards, because it was increasing at decreasing rate, now the function starts rather decreasing, because there will come a point where it will start decreasing, and that will come when right after the point of x where the first order derivative was equal to 0. All right, so basically this function was this function had only maxima, right? And it also meets this condition that at this maxima the first order derivative is 0 and the second order derivative is negative at this point, right? Now consider this function which had only local minima. So in this case, you see the function is decreasing with each increase in x. The function is decreasing. Basically, if we increase the value of x, y is decreasing, but y is decreasing at a decreasing rate. So the second order derivative will be positive. Please try to understand. The first order derivative will be negative. I understand for this function, but if you calculate the second order derivative, that will always be positive, because you can see it is decreasing, but it is decreasing at a decreasing rate. It's not decreasing at increasing rate. It is decreasing at decreasing rate. Had it been decreasing at a constant rate, it would have looked like this, right? So it is decreasing at a decreasing rate. So second order derivative will be positive. So and its first order derivative is 0 here, and at this point its second order derivative is positive. So it's local minima, right? So these conditions are true. Now let me come to the point. What is saddle point? Okay. One more thing. Wait. I'll tell you one more interesting point. So why f dash x equals to 0 doesn't guarantee that at that particular value of x where f dash is equal to 0 doesn't tell you that it's a maxima. Suppose if the function would have looked like this, graph would have looked like this. In this case, you see at this point, first order derivative is equal to first order derivative is 0 at this value of x star x, which is equal to x star. But the function doesn't have this value as maxima. It's still, the value y still increases, keeps increasing with successive increase in x, right? It keeps going up. So this is not the maxima. So this is the necessary condition, not the sufficient condition. The sufficient condition is second order derivative. Second order derivative still is not. The second order derivative is still not negative here, right? So if you take the second order derivative for all the values of x less than x star, in that case second order derivative will be negative. And if you take the second order derivative for all the values of x greater than x star, it will be positive. So in a way, this doesn't satisfy the condition, and this is also visible. This is also evident the way the graph looks, right? So we call this inflection point. Now let me talk about the saddle point. Okay. Now saddle point. Okay. So let me draw that seat which is placed on the back of the horse. So suppose okay. Right? This is how the saddle looks, right? ये हम घोड़े के ऊपर रखते हैं और इसके ऊपर आदमी बैठता है, एक टांग उधर करके एक टांग इधर करके, ठीक है? And this is the three-dimensional figure, right? So we have to draw three axes. So suppose this is the z-axis, which will consider the dependent variable. This is one x-axis which is going to take one independent variable, and suppose this is the another y-axis which is going to take second independent variable. So we have two independent variables. One is going to be placed. So one is x, another is y, and z is the output. Okay. So the function is going to take these as the two inputs. Now you see. Now you can see that this saddle at this. So if, suppose if I take the partial dot derivative of z with respect to x, let's keep y as a constant. In that case, if you see, please try to understand. Please try to imagine, visualize how this seat which we place on the back of the horse looks like. Okay. So basically, when person sits on the seat, this is one point where first partial order derivative of z with respect to x will be equal to 0, and this is the same point where first partial order derivative of z with respect to y will be equal to 0. Why? Because you see, please try to imagine this in three-dimensional. Only then you will be able to understand what I am trying to convey. Now you see, when I increase x, right? When I increase x, this is going to give me the minima, right? If I increase the value of x in this direction, and the z is this, right? So function is going to witness minima when I increase the value of x or change the value of x, right? Or like not necessarily increase the value of x. So suppose if I am going to change the value of x in either of the direction, basically it is going to give me the minima, right? You okay with that? But if I take the first order derivative of z, first partial order derivative of z with respect to y, in that case, try to think in this way. In that case, this you have to go as a. In that case, it is going to give maxima. The first partial order derivative of z with respect to y will be equal to 0 at this point, but the second partial order derivative of z with respect to y will be negative, because you can see that this is the maxima. Please try to understand. You can drop your comment also if you have still question. So it's like this, na? Like I'm going to put my like एक leg आदमी उस तरफ रखेगा, एक leg इस तरफ रखेगा, और जब उसमें बैठेगा तो this thing will be maxima, ना? This thing will be maxima. Whereas in this case it is minima. Whereas in this case it is maxima. In this case it is minima. Saddle. So this point will be called this point where the first partial derivative of z with respect to x and also the first partial derivative of z with respect to y is equal to 0. But where the second partial derivative of z with respect to x will not be equal, will have an opposite sign as the sign of the second partial derivative of z with respect to y. So in this case, the second partial derivative of z with respect to x is positive, because you see it is decreasing at a decreasing rate. Whereas in this case, maybe I have not drawn it in the right way, but you can see the picture of saddle in Google. How does it look like? You will see that it's again a smooth curve, and it is increasing at a decreasing rate. So it will be maxima if we look at with respect to y. Okay, if we look from the standpoint of y variable. So saddle point is one such point where the second partial derivative z with respect to x and y separately, it will look very different. It will have a different sign. Either one will have positive, other will have negative, or one will have negative, other will have positive. So, and one classic case is this. Say suppose the function is y square minus x square. So in this case, first order derivative will be 2y. For if first order derivative with respect to y will be 2y. First order derivative with respect to x will be 2x. Second order derivative with respect to y will be 2, and second order derivative with respect to x will be minus 2x, right? Because it was minus x square. It will be minus 2. So first order derivative will be 0 at if the y is equal to 0, right? So this 2y will be equal to 0 only if y is equal to 0. This minus 2x will be equal to 0 only if x is equal to 0. So at 0, 0, basically at x, y, 0, 0, this 0, 0 will be the saddle point. Why? Because first order derivative of z, first partial order derivative of z with respect to x is 0. First partial order derivative of z with respect to y is 0. And if you see the second partial order derivative of z with respect to x is minus 2, whereas second partial derivative of y with respect to second partial derivative of z with respect to y is again 2. So it's one is giving you minus 2, another is giving you 2. So each one is having a different sign, plus and minus. So that's why this 0, 0 will be a saddle point. This is a typical case where the function doesn't have neither maxima or minima. So it doesn't have local extreme point, right? So this was it. I tried to be as quick, as diligent, as detailed as I could have been. If you have any questions, please drop a comment. You can call me also. You can drop a comment and we can talk. We can have a live session. Thank you so much for your time.